Hello, my name is Keren Garcia, and I currently work with the discrete computation team. Today, I'll be discussing charting courses in 2D and 3D motion planning in robotics. To give a brief outline of today's talk, I'll be discussing motion planning, major concepts in motion planning, methods to approaching the motion planning problem, and I'll give some applications at the end. So, what is motion planning? Motion planning is the process of finding an efficient path for a robot to move from one point to another while avoiding obstacles. Now let's move on to the motion planning problem. The problem can be simplified to how can a robot move from point A to point B without colliding with obstacles? That is, what is a valid path and what is an invalid path to get from this location to the other location that we are trying to get this robot to. So let's start with some concepts. One of the most important things to begin approaching this problem is deciding what kind of a robot is being used and for what. There are many different types of robots. Depending on the application that we're trying to solve this problem for, a robot can have many hinges, no hinges. It can be a mobile robot. It can be a robot that is traversing through a very crowded space or not crowded space. So this is one important major concept when approaching this problem. The next is the workspace. So the workspace in motion planning is the physical space where the robot and obstacles exist. So this can either be a two-dimensional or three-dimensional environment. Then we have the configuration space. And the configuration space is where the robot can move around after we expand the obstacles in the workspace by the dimensions of the robot that we are using. So in this case, in this image, you can see compared to the previous image, this space now has the objects that are expanded by the dimensions of a robot. Now let's talk about some of the challenges in motion planning. One is high dimensionality, meaning that there could be many joints or parameters to the robot that need to traverse across the workspace and that need to be taken into account when solving this problem. The second is that paths can be hard to compute, especially when you have an environment that is non-convex that can have many different obstacles in the way. The third is real-time constraints for dynamic environments, meaning that a path may need to be computed quickly depending on the task that the robot needs to accomplish. And sometimes there is not enough time for this to be computed quickly. The last is optimality versus computational speed, meaning do we want the most optimal paths for the robot to traverse or for the path to be computed quickly? So now let's move on to how we approach and solve the motion planning problem. So, motion planning algorithms. There are many different approaches to solving the motion planning problem, and some of these are graph-based methods, sampling-based methods, optimization-based methods, and modern methods, to name a few. So let's start with graph-based algorithms. These algorithms basically use graph search algorithms to compute discrete paths in the robot's state space. This type of planning can be divided into two different main problems. The first is how do we transform the initial problem into a graph? And the second is how do we find the graph corresponding to the best possible solution? So if the graph that is representing the space in which the robot is traversing is constructed correctly, then these types of algorithms or planners are able to find a solution, assuming that a solution exists in this space. However, having to transform the entire space into a graph in order to find the best solution means that the algorithm can be computationally heavy, especially in environments that are very complex or that require a large number of graph nodes. Then we have sampling-based algorithms. These types of planners, such as the PRM, the probabilistic roadmap, RRT, the rapidly exploring random tree, are the most common types of planners to approaching the motion planning problem because they're very quick and very effective even in complex environments. In this type of algorithm, the configuration space is randomly sampled. So you follow a probability distribution, such as the Gaussian distribution, and you take sampling points throughout the space. For each sampling point, we check whether the robot's configuration space is collision-free or not. If it is, then it adds the configuration to the graph of possible configurations and connects it, if possible, to the other configurations that are already existent in the space, in the graph that we are creating. So once this graph is constructed, the algorithm then can determine a collision-free path that connects the initial location to the final one. Sampling-based planners turn out to be very fast, even in high-dimensional configuration space. However, in these types of algorithms, there is no optimization. So the smoothness of the path or the kinematic profiles of velocity, acceleration, and jerks of the robot are not taken into account, and this can result in higher consumption of the robot. Then we have optimization-based algorithms. As I mentioned before, sampling-based planners are very fast and effective, but they have major limitations on the final smoothness of the paths and optimality regarding kinematic constraints to the velocities, accelerations, and jerks of the robot. This means that the final trajectories will be executed by the robot are worse, in the sense that they'll take longer, they're not necessarily safe, and they usually take higher execution times. So for this reason, algorithms such as CHOMP, the trajectory optimization, and STOMP have been developed to compute the final trajectory as a solution of the optimization problem. So they consider the cost function with various constraints. This means that the main disadvantage in these optimization-based algorithms is that the planners turn out to be computationally complex. So they grow considerably in time compared to sampling-based algorithms, making them have longer planning times and making them unsuitable for planning online. Another major disadvantage that is present in these optimization-based algorithms depends on the initial conditions. So this leads to the trap of local minima rather than global minima, which causes an increase in failure rates compared to sampling-based planners. Then we have the modern or hybrid algorithms. These post-processing algorithms have the purpose of combining the advantages of both sampling-based and optimized-based planners. So in these algorithms, there is the generation of an initial collision-free path by using the sampling-based algorithms, and then this path is used as the initial condition put into the optimized-based algorithm in order to obtain the final, most optimized trajectory. With this procedure, it is possible to plan a final optimized trajectory because of the optimization that is run after the sampling-based planner. Computational times in these types of planners turn out to be quite high because there are two algorithms that you're running, but with the proper combination, they can be optimized as well. So basically, if the first sampling-based step is fast and the second one can take a shorter time because it is already optimized. Now let's talk about how motion planning works. So first, we need to model the robot and the workspace. From then, we need to build the configuration space, choose an algorithm, check for possible collisions, refine the path, and then execute the path and possibly have to optimize the path depending on how the plan is executed. So what are some of the applications of motion planning? Motion planning is used in autonomous vehicles, as well as industrial robots, drones, and humanoid robots. Now let's discuss one application. So in the case of a mobile robot, if we have a mobile robot that is provided information throughout a floor plan, in this case, we're traversing a living room. Say we're using this mobile robot to clean our living room. Now let's get to the workflow. The first thing we can do is translate our living room into a 2D workspace. So here you see the couch, the side tables, etc., and the mobile robot. From then on, we create the configuration space. This is basically simplifying the task by representing the robot as a reference point and expanding each obstacle in our living room by the dimensions of the robot. So this enlarged furniture is now the configuration space. From here on out, we can try to find an efficient path. In this case, I'm using find shortest curve to find an efficient path through the configuration space. So now that we have this efficient path from the previous page, I can translate this into a plan for the robot, basically determining the distances for the robot to travel and what angles it has to turn. Now we can then feed this plan to the robot, and we can visualize the robot following the plan. It will move along the calculated path, and it will adjust the course and avoid collisions with the furniture based on the plan that we had given it. So, in summary, motion planning involves a collision-free path for a robot to move from point A to point B. One of the central problems in autonomous robotics is motion planning, especially in navigation, manipulation, drones, production lines, etc. Some of the main concepts to take into account when approaching the motion planning problem is the workspace versus the configuration space. And as we have seen, there are various types of algorithms to approach motion planning. And lastly, one of the biggest issues is balancing optimality, whether we want the shortest or the smoothest path for the robot to use versus the computational efficiency. If you're interested in more talks from the discrete computation team, there is a talk on Friday at 8:30 in the morning, From Puzzles to Graphs, Coloring Your Way Through Sudoku. And if you're interested in more content like this, you can follow us on Wolfram R&D YouTube channel at Wolfram RD. Thank you so much for attending the talk. If you have any questions, feel free to ask, and I will answer them as best as I can. The notebook is also available to download if anybody wants to see how the problem that I showed was worked out as well. Okay, I see a question from Patrick, wondering if using onboard sensors is useful in gathering photo images, determining the angles needed for course changes. I'm assuming that you're meaning like if we used sensors that would have a live feed of the course as we were, of the environment as we were traversing the space. That would be one way to determine the path like in real time, which is something that can be done. But in this specific presentation, I did not cover that. But I do know that there are some algorithms that are computed as you are traversing the space. So if the robot itself had a way to look at the actual space as it was moving, then you could make more real-time computations. Is it the same principle for scanning a 3D compartment by a drone? Yes, it would be a similar principle. So this example that I showed is basically the same principle for, or the most simplest way to approach the motion planning problem for robots in 2D and 3D environments. So that would cover autonomous vehicles as well, drones, etc. Good question. Oh, you're thinking robot vacuum, snapping photos as it moves. Yeah, I guess that would be similar to if the mobile robot had like a live feed. I would say, however, I feel like that would take some more time because you would have to feed the photos to whatever it is that's computing the path for you. So there would be maybe some type of lag, or what we would consider lag, right? Because it wouldn't be like automatic. Or it could be automatic, but it might take some time doing it that way. in the future, the hope is also to that this example and a 3D example will be available as like a workflow in the documentation. Yeah, so I'm not sure if it's very clear from this image. Maybe if I make it a little bigger. But here you can even see like the mobile robot itself is like turning angles according to what we feed the robot based on like the plan that I put on it. So like you can see here, the robot turns, like this is the front of the robot and it's turning as you're going. This is a very like basic example, but again, thank you everyone for attending the talk. And thank you for the questions. I hope that you all enjoyed the presentation. And like I mentioned, there are more talks from the discrete computation team. There's a Sudoku one tomorrow at 8:30 in the morning. And if you ever want to see more content similar to this or more technical, feel free to follow us on Wolfram RD on YouTube. We post there pretty often. So, and feel free to message questions and whatnot. But thank you. Thank you, everyone.